And so let's now do some real computational problem on the standard normal distribution. And so let me start out with a formal example here. And so do expect that in this example, I am going to break that down into multiple questions, and we're going to learn different experience in doing computation on the standard normal distribution. So as the beginning of this example, let's start out simply by having an n01 being given. And so we're given a standard normal distribution. And so I highly recommend that anytime that getting into doing a normal distribution or standard normal distribution specifically, or just generally any normal distributions, right at the moment we are given with that information that we know we're on a bell curve with mean and with standard deviation, etc., start having for yourself an empty bell curve, getting ready for action. So here's my empty bell curve, because we definitely need to make a lot of shading area here. So this empty bell curve now furthermore is known to have mean in the center at 0 and standard deviation. Not trivially seen through the picture, but we can note it somewhere here because it's given, and it's bell curve. And so here we label our horizontal axis. Here is the z-axis. So that's the given information. So now the first question I'm bringing up now is, let's find the probability where our z-score, and yes, I already explained, and we already looked through that the whole purpose of standard normal distribution is this is also a perfect place for all the z-scores. So now it's completely legal to say either you can call it the z random variable or just simply z-score. So find the probability that we having on this bell curve here, we're having z-score anywhere from -1 to 1. And so now, before we even rush into any further thoughts or any further thinking, before making any of that, let's just first make a sketch. So we don't have to be too worried about scaling. So -1 is somewhere to the left-hand side of the center 0. It makes sense that way. And +1 is another value being somewhere to the right-hand side of 0. So the center is here, the 0, the mean value. And so now this probability question here, on this bell curve, let's find the accumulated probability where our z-score or our value of the z random variable takes place inside of this interval. And I have said up to this point many times that a probability in the concept of a continuous random variable can be graphically represented by a shading area. So here we're having that shaded area going exactly inside of this interval. And so now, as soon as I finish drawing this, making the drawing right here, making the sketch right here, then anyone viewing this video should have start having in mind some the formulation of the answer already. The answer here is quickly 68%. And I didn't even have to pull out my calculator, and I knew the answer so quickly. So how did that happen? Well, once again, z-score -1 represents this point here on the left is 1 standard deviations, and below mean. And similar explanation, but this z-score +1 is 1 standard deviation. Or now I should have used a sigma for standard deviation, no longer lowercase s. So 1 sigma below mean is here, and 1 sigma above mean. That's what z-score +1 is all about. And so, does that recall? Do I start recalling some known facts here? We can immediately use the empirical rule to give that answer. So once again, empirical rule that we've learned a little while ago now kicks back here and explain for this problem. And see, before, when we first learned about the empirical rule, I did make it clear that the empirical rule is only valid when we're working on a normal distribution, and here it is. So it's a perfect place that we can pull out and use the empirical rule again. And so the empirical rule stated that the amount of data, there are 68% of data, or about 68% of data being inside of the interval between from 1 standard deviation below to 1 standard deviation above mean. And remember back then I call this interval, it's being the interval within 1 standard deviation from the mean value. And that's the reason how we come up with that. No need for any special math. And again, in the same example of the same video lesson here, we're still being on the standard normal distribution. And so even before I write down the next question, let's go ahead and draw for ourselves an empty bell curve. And we call this bell curve the standard normal distribution. The random variable labeled here is the z variable. And the center is right at 0. We have a known standard deviation being 1. And this is the PDC for that. And constantly remind yourself, even though we don't need to shade it in, but the total accumulated area here is 100%. So, question B of the example now. We want to find the probability where our z-score is anywhere from -1 to, how about, 2. And so once again, we don't need to make any further thinking yet. Simply just after writing down the question, the first thing we need to do, put down the value that seems to make sense here. So -1 is here, somewhere to the left-hand side of the bell curve center, and +2 this time is somewhere further out, about twice as far the length. That's where we can locate properly the value 2 or z-score 2. But then, as far as the actual answer, here we're looking for the probability where our z-score being inside of this interval. And so, we already learned that this is going to be represented by, that probability answer here is going to be represented by accumulated shading area. And once again, this -1 here, it's a z-score being -1, but it also means we are 1 standard deviation below mean. And this other value right here, this other z-score or other value of z right here is being precisely 2 standard deviation above mean. And so it looks like it's a convenient place again to use your empirical rule. And so it looks like anyone viewing this current video here can see that my intention for this video here is to remind you about how useful the empirical rule can be again when we're working with the continuous random variable, and specifically now we're studying about the standard normal distribution. And so as another reminder, and there are many ways of arguing. This is just my one way of how I argued it. But on this bell curve right here, my area is not exactly symmetric. So at least I have something from the center out to one end right here. Then that area of mine there should be labeled as a 68%, but over 2. So why did I bring up 68? Because it's relating to 1 standard deviation away, but only on 1/2 side from where the center is. And so 68 over 2 and 68%. This other side from where the center reach all the way out to my other end of the interval, and you can see that I'm attempting to make a right arrow even though my marker is not making a very well done job there. But this is as far as the distance from the mean right here, then this is 2 standard deviations to the right hand side, but at least once again it's relating with the rules about 2 being 2 standard deviations away. And so the rules about 2 standard deviations away reminds us that we should have, in that it's relating to the 95% interval. But here we're not looking at the complete 95% interval, we're only halfway since we're on only one side, so 95 over 2. And then the shading of the area that we drew here is indicating for us, and just simply look at the area. Naturally enough, it's telling us that we need to accumulate all that area on the left and with the right hand side. And so one piece of us here that we have, one piece of ours that we have here is being a 68 over 2. Another piece here is being 95 over 2. And right now I'm writing these in percentages. And so, but we need to add them because it's the idea, again, we're accumulating the area. And so 68 over 2 is the 34%. That's for the piece to the left. 95 over 2 is the 47.5%, is the piece to the right hand side, and we are accumulating up these two pieces of area. And so in the end, we're looking at a total amount of, out of the entire curve, which is supposedly 1 or 100%. This shaded area, of course, cannot be as big as 100%, but it's now being 81.5%. And I do believe I forgot one note in the earlier problem, and here I would like to correct this. But so empirical rule, this is our answer just fine. But now when we start switching to use a formal probability, and we're working formally on a standard normal distribution curve, or in general any normal distribution, then start using the final answer as a start writing the final answer as a decimal. And so here we're looking at 0.815 here. And so 0.815 is usually a lot of professors and even a lot of online homework assignments are going to be looking for that form here instead of 81.5. Even though writing your final answer as a percentage is not incorrect, but now it's more preferable that we're writing the final answer here as a 0.815. And so allow me to make a note in my problem earlier. So this note specifically for the problem we did earlier, that for part A, yes, we did find the answer, okay, was 68%, and you can always roll back to that part of the video, but now it should have been written, it should have been written as 0.68. But admittedly, either way of the answers here are not wrong. It's just when we're formally working on the bell curve here, and like I said, a bigger majority of professors and statisticians prefer to write the answer here in decimal. And again, on the same bell curve right here, before I write down any new question, let's draw for ourselves that nice bell curve right here. Never skip the bell curve, never skip drawing the bell curve. Sigma equals 1, 0 here. And I have to really emphasize the importance of drawing the bell curve and make the shading for itself. Over years of teaching stats, you know, I keep a lot of time and very big amount of time that when my student, any student of mine coming to office hours seeking for help about these, and as soon as I look and I found out they didn't draw the bell curve, I immediately, first thing is to ask them to draw a bell curve. And once they've got their bell curves drawn right here, they can find an answer for themselves, and without my help. And so never look down to drawing and making the sketch on the bell curve right here. And so now you got a bell curve for the standard normal distribution. Question C here, let's look at about, in my own creativity right here, let's find the probability where our value of the random variable z is being inside the interval from -3 to anywhere less than or equal to about -2. Okay. And you can see that here I'm just giving, even though we already studied about the bell curve a little while ago earlier in the quarter, but here let's resurface with these problems so that it's re-emphasize your skill right there, and we can briefly review all of that. And so once again, this question here, before we even simply, as soon as we wrote down the question, simply just put down, and we don't need to be too worried about how precise is, how big is precisely a standard deviation 1. And that's big enough. No one's going to hurt us for that. So negative 1, negative 2, and negative 3 is here. And we are looking at the shaded area from here, negative 3 to negative 2. And so the shaded area came out as a graphical translation of this question. Find the probability where our z values being inside of that interval. And so now, once again, this negative 3 z-score is indicating that that value specifically on this bell curve here stays 3 standard deviation, 3 sigmas below mean. And this other value right here, the upper end of my interval, of course, interval always read from the left to the right. So on the left is the low end, to the right is the higher end. So the upper end being a negative 2, this value there is indicating we are 2 standard deviation, but still below mean, to the left of the mean here. And so we're 2 sigma below mean. Okay, but I've been making these interpretations simply just to help people or any viewer to this video recognize that we can, again, we have the rules, the empirical rules that help us handle all of that. And so, and when it gets to using the empirical rule, I never said that my solution has to be the best solution, my approach has to be the fastest solution. It's just the solution that I feel that, you know, throughout my years teaching, it's easiest to explain for anyone. But of course, you can always find a much more effective solution approach based on the empirical rules that a lot faster than mine. And I would love to see that you can be faster than my work here. But so the empirical rule said that if we go from the center out to 2 standard deviations away, then that complete interval supposedly 95%, but here we don't go the entire interval. If we go to a complete 95, then it needs to go from negative 2 to positive 2, but here we only half side of that. And so this part right here, this empty space from the center out to that bottom side is a 95 over 2. So it's a 95 over 2. 95% over 2. And like I'm saying, my explanation here is not the only way to explain, even though we're all using the empirical rules to work with. And then, if we go from the center out to 3 standard deviations away, let me make a dotted line right here to indicate our boundary, but I'm drawing a longer arrow. Going from the center, the mean value, out to the further end of our interval. That longer interval there supposedly, according to the empirical rules, takes 99.7% of data. But that complete 99.7, as a matter of fact, needs to be this complete symmetric interval up to here. That's 99.7. But here we actually only half side of that. So now allow me to barbarically erase by hand the other part away, because I just want to indicate that we only half side of that complete 99.7. So we actually need to divide this by 2. And so there's a 99.7% divided by 2. And think about it this way right here. Here's my approach, but I see the 99.7 comes from a longer arrow, meaning it should have covered more area. And then the 95 over 2 is inside of the 99.7 over 2. And so we need to find that remains area here. But this remain area we're shading in black right here is outside. It's not in the empty space. This empty space here is 95 over 2. But this area is outside of that 95 over 2. So, but still inside of the 99.7 over 2. And so in that way, I'm going to need to subtract out the empty space. But like I said, if you don't like my explanation here in this video, there are other ways of approaching it. As long as you understand the nature of the bell curve and understand how empirical works, feel free to find your own way that what works will be what works. And so 99.7 over 2, and take away the empty space being 95% over 2. And that now, after the math, it gives me, my calculation comes out being to 0.35%. And once again, don't forget, now when we're formally working with the normal distribution, then start writing our answer as a 0.0235 in decimal value. And this is our final answer. All right, and up to this point, viewing this video of mine right here, and you can see that the more example question I brought up in this particular example in our video here, then you can see that it's mainly intended to use the empirical rule, and the further you understand how important the empirical rules can help you solve a normal distribution problem, and specifically right now easily on the standard normal distribution problem. So on that same bell curve, again on that same N01, the standard normal distribution, go ahead and have for yourself an empty picture again. Really get into that habit of drawing an empty bell curve for me. Okay, and here we already had a mean specifically at 0, population standard deviation being 1, and the value, the variable on this horizontal axis here is the z variable. Okay, and so here's my question. So we should be at question D right now, but question D now is continuing from the earlier question. Let's find the probability. So have your empirical rules in mind right now. Find the probability on this bell curve where we're having a z-score going anywhere from 0 and less than or equal to 1.5. Okay, so ladies and gentlemen, whoever viewing this video of mine, if you really want to have some real good learning about and get real fluent about how to use the operate on the bell curve, I highly recommend at this point, after you make your drawing and your sketching, so 0 is here on the bell curve, 1 is about here, 2 is about out here, 1.5 is about here. And just as usual, we're going to be making a shading between anywhere from 0 to 1.5. That's what the question asks. But now I highly recommend if you can pause the video, make for yourself a brainstorm for yourself and try to find tons of different ways how you can find this answer right here. And once you come up with your own answers, then come back and go on with this video to find out what my answer is and compare your answer with my answer. All right, and at this point, I hope you did pause the video and did some work on your own and have for yourself some answer, some thought to be the answer right here. And so here's my answer. The answer to this, I don't know. Wait, what? I don't know? I thought I'm teaching stats here, but I don't know the answer to this problem that I put up myself. My intention here is that if we are using the empirical rules attempting to solve this problem, then this is where we have reached to the limitation. So this is a limitation of the empirical rules. All right, so what's that limitation of the, we've reached to the limitation of the empirical rule. So what's that limitation? So that I, being a teacher here, but I have to say I don't know how to find the answer if we're only using the empirical rules for this. Simply because empirical rules can help you to handle areas problem when you are neither whole z-score, like say either z-score 1 or z-score 2, z-score -1, z-score -2, or z-score -3, and so on. But empirical rules do not know how to handle those area problem when you're at a z-score like this with a decimal. But the big word is waiting ahead for us right here. We have to be able to overcome with this. But so now empirical rule is just simply not going to work. So we need to promote new methods right here to handle this kind of problem where we're going to have to be a lot more flexible than whole value z-scores.